Calcium is also concentrated outside the cell. Discussing these ions, sodium, calcium, and potassium, because these are the principal ions that determine the formation of an action potential. This is how cells within the muscle system and nervous system communicate through action potentials. Another type of ion that's located principally inside the cell are proteins. Proteins tend to carry a negative charge. These are larger molecules. And because they're produced inside the cell, they're too big to cross the cell membrane, they're concentrated inside. Now, because all these particles have a charge, these are polar ions, okay? Meaning they have a charge or separation charge. And therefore, they don't easily cross the cell membrane. Unless there's some type of pump or channel that allows them to cross. And of course, if it's a channel, it's got to be open. Now, one of the types of transmembrane proteins that are responsible for maintaining this gradient, the high concentration of sodium and calcium on the outside, potassium on the inside, are active transport pumps. And one of the principal active transport pumps is the sodium-potassium ATPase pump. An active transport pump requires ATP, it requires energy to operate. And so you have active transport pumps sitting along the cell membrane that pump sodium out. In fact, typically they'll pump 2 or 3 sodiums out in exchange for pumping 2 potassiums in. Now, sodium potassium ATPase pumps are located not only along cardiac muscle cell membranes, but typically all the cell membranes of the body. And for that reason, throughout all of our cells, we have a higher intracellular concentration of potassium than extracellular concentration by a wide margin. And there are other active transport pumps that help to maintain concentration gradients. So one mechanism for ions to move across the cell membrane is through pump activity. We also said that another mechanism is the presence of ion channels. Like pumps, ion channels are ion specific. They're specific for particular ions. For instance, you may have transmembrane proteins here that form an ion channel specific for potassium. Okay? Now, these types of channels made up of transmembrane proteins that allow specific ions to cross, if they're always open, they're called leakage channels. And so this leakage channel would be specific for potassium. And if potassium were allowed to freely move across that leakage channel, in which direction would potassium move? Would it move from inside the cell to the outside, or from outside to in? So you think that potassium would typically move in this direction through a leakage channel against its concentration gradient. Now, if there is a higher concentration of potassium on the inside than on the outside,
then it would go out.
It's going to passively diffuse from greater to lesser concentration. So it would tend to move out like this. At the same time, if you had any leakage channels for sodium, in which direction would sodium move? Yeah, it would follow its concentration and tend to move into the cell like this. Now the truth is that most of the ion channels are gated, meaning that the gate will typically be closed and not allow passage of ions, except under certain circumstances. There are very few leakage channels. In fact, because there are so few leakage channels, the sodium potassium ATPase pumps kind of restore ionic conditions when ions do leak across. The sodium potassium ATPase pumps pump those ions back into or out of the cell. Most ion channels, as I stated, are gated. So they have one or two gates that cross the channel, and when that gate is closed like this, let's suppose this is a gated channel for sodium, or let's say it's a gated channel for potassium, then as long as that channel is closed, potassium can't exit. It can only leave the cell if in fact that gate opens. Most gated channels are either voltage-gated channels that open in response to a change in transmembrane voltage, or they're ligand-gated channels. That means they open only in response to binding of a chemical messenger from ligand. Now, because of the particular concentrations of ions inside compared to outside of the cell, there's an electrical potential that can be measured across that cell membrane. We call that a transmembrane potential. A transmembrane potential just means there's a difference in charge across the membrane, with the inside of the membrane being negatively charged compared to the outside, which has a more positive charge. That makes sense. Because these pumps are pumping 3 sodiums, positively charged ions, to the outside, okay? And at the same time only pumping 2 positively charged potassium ions to the inside. So that in and of itself creates a difference in charge. Also, the fact that these negatively charged proteins are confined to the inside of the cell contributes to this electrical potential. If you took a voltmeter, one of those things that has a dial, and connected an electrode to the outside of the membrane, another to the inside, you could measure that difference in charge. At rest, it's typically about negative 90 millivolts, or somewhere close to that. Meaning that the inside of the cell is more negatively charged compared to the outside. Typically, what happens with these voltmeters is that we consider the outside of the cell membrane, well, currently assigned at a value of 0, and so the inside is negative 90 millivolts compared to that outside value. And so this would be a reading at rest. Because there's a difference in charge, the inside is negatively charged compared to the outside, we say that the membrane is polarized. And that transmembrane potential equals negative 90 millivolts at rest. We have a graph. Now on this graph, this mark here would be 0 millivolts. The transmembrane potential at rest would be negative 90 volts. Now, when a cell like this undergoes depolarization, what we're saying is that the cell becomes less polarized, that the inside becomes less negative. So if this is the value at rest, with depolarization, the transmembrane potential is going to move towards zero or beyond. We call that depolarization. And of course, both muscle tissue and nervous tissue has the potential to depolarize, and it kind of reset itself and repolarize like this. That process, depolarization and repolarization, represents an action potential. Okay? And it can spread like a wave. If a certain segment of the membrane depolarizes, it will spread then to the other end of the cell. Now, in cardiac cells, as they depolarize, that depolarization triggers contraction. And coupling of the two events is called electrico-mechanical coupling. We talked about some of this in A&P 2. Okay? So this is simply the foundation upon which we're going to build today, this concept. Let's turn on the magic computer. Let's pull down this thing. Yep, sure. So when I first came here, I'm going to tell you this. One of the first teachers that I had on faculty was Coach Brooks. Okay? Coach Brooks was a speech coach. He taught all of the speech classes. And I remember I used to sit down in the cafe and talk to him at lunchtime, because basically I didn't know anybody else. And I introduced myself. And what I liked about Coach Brooks is, at the time, he must have been like 80 years old. And someone who's that old has lots of words of wisdom that they can provide a young whippersnapper like me. Okay? So, I was asking him for any advice he could give me with respect to teaching in a classroom. And he said, you want to start off like this. Tell them what you're going to talk about. That's what we just did. I told you what we're going to talk about. Then he said, get up and talk about it. That's what we're going to do now. Get up and talk about it. And he said, when you finish, tell them what you just told them. Now, someone. Yeah. That's what Coach Brooks said. He also said, move around a lot. He uses the triangle method. Walk to one side, address those folks. Walk to the other side, let them know you care about them. And then move perhaps to the front, to the apex of the triangle. Right, I got you covered. Okay. So everybody knows they're getting a little bit of attention. Yeah. And he said, don't be afraid to use your hands. Yeah, yeah. Okay. So, a little words of advice. Interestingly enough, Coach Brooks was forced into retirement. The last time I saw him, I went to my cardiologist office. And this is an office. It was a cardiologist I used to cross cover with. And I saw that Dr. Brooks was a patient of this doctor. And I said, hey, Coach Brooks, good to see you. He didn't remember me at all. Negatory. Yeah, yeah. He may be dead now. He may have gone to the great beyond. May rest in peace. All right. Last time we talked about the structure of the heart, but we didn't talk about the electrical circuit inside. There's a circuit, electrical circuit inside the heart, called the intrinsic conduction pathway. These are specialized cells responsible for initiating and conducting an action potential. And by conducting that action potential, first throughout the cells of the atrium, then it's carried on into the ventricles, it triggers contraction. So this is a network of specialized, what are called algorithmic cells responsible for initiating and distributing an electrical impulse or an action potential to resting myocardium. And when it distributes that action potential, those cells contract. Now, algorithmic cells, these cells, their main function is not to contract. Their main function is either to initiate or conduct the action potential to other cells. Okay? And they do so without any external stimulation. Okay? That's why they're called autorhythmic. They can generate an action potential without being stimulated from outside. Now, the autorhythmic cells of the SA node generate action potentials at a constant rate, generally between 60 and 100 times per minute. And therefore, the SA node is called the heart's pacemaker. Every second or so, it generates an action potential, and that action potential is then going to spread through the conduction pathway to the rest of the heart. Notice that autorhythmic cells, like the cells in the SA node, don't have a stable resting membrane potential. The membrane potential is constantly drifting up toward what's called a threshold. And when it reaches the threshold, that cell suddenly depolarizes. Following repolarization, you see that drifting baseline back to threshold, and the cell fires again. These drifting resting membrane potentials are called Casemaker Potentials. Okay? So it says the autorhythmic cells of the SA node initiate action potentials at a constant rate because they don't have a steady resting membrane potential, a flat resting membrane potential, like other cardiac muscle cells do. Instead, the membrane potential is always drifting toward the threshold potential, which generates another action potential. And that cycle of drift and fire repeats itself over and over again, typically at a constant rate. If it's the SA node that's generating those action potentials, the rate is normally between 60 and 100 beats a minute. Here's that intrinsic conduction pathway. The SA node is located along the roof of the right atrium. Okay? It's composed of algorithmic cells. That cells are capable of spontaneously generating action potentials. You have another node here along the interior aspect of the inner atrial septum. This is called the AV node. Now, when impulses are generated within the SA node, they travel along specialized atrial muscle cells, along specialized pathways toward the AV node. These three pathways from the SA node to the AV node are called internodal pathways, or internodal tracks. There's another track that passes from the SA node to the left atrium. It's referred to as Bachman's bundle. So that's going to deliver that electrical impulse to the left atrium. Now, all the while, as this impulse is traveling toward the AV node, it's also spreading out laterally and causing depolarization of typical atrial muscle cells. So it's spreading down both toward the AV node, and at the same time it's spreading laterally, bringing about depolarization of the upper chambers. When that impulse reaches the AV node, conduction velocity slows. Okay? And then the action potential is going to pass through this structure called the AV bundle, or the bundle of His. This is a specialized pathway that carries the impulse into the vesicle, specifically into the top of the interventricular septum. That in normal hearts, this is the only pathway through which electrical activity can be conducted from the upper into the lower chambers. You have a fibrous band that surrounds this AV junction and all other sites that prevents any transmission of impulses from the upper to the lower chambers. This is the only route through this bundle of His, or AV bundle. So from the AV node through the bundle of His, it's going to enter into the interventricular septum, and that bundle of His is going to split into a right bundle branch and left bundle branch. The right bundle branch is going to bring that wave of depolarization into the right ventricle. The left bundle branch is going to deliver that wave of depolarization to the left ventricle. The branches of these pathways are called Purkinje fibers. So these extensions of the main bundle branches are called Purkinje fibers, and the impulse spreads very rapidly through Purkinje fibers, so that we get simultaneous depolarization of the left ventricle and the right ventricle at the same time. So that as the wave of depolarization spreads into the ventricles, they both depolarize and contract simultaneously. Here's another picture of the conduction pathway. All right, this is a picture very much akin to what I drew on the board. Let's turn off the lights. Get a little more comfortable. Yeah, it's like a movie theater. We can see that this is the cell membrane, a bilayer of phospholipids. These are the intracellular ions. Here are the extracellular ions. So it says at rest, all cells have an electrical potential, a voltage across the cell membrane caused by a separation of charged particles, or ions. Okay? The intracellular space is negative in comparison to the extracellular space. Because of this, we say that the resting membrane is polarized. Negative on the inside, positive on the outside. And that's polarized at rest. The principal ions which determine this resting membrane potential are the same ions that are going to determine the action potential: potassium, sodium, and calcium. We mentioned that an active transport pump, meaning a pump that utilizes energy, ATP, typically pumps 3 sodium ions out of the cell in exchange for 2 potassium ions into the cell. Because of this differential, 3 to 2, as well as the fact that the intracellular space contains negatively charged proteins, okay, we have this negative intracellular potential. Okay. Again, not only within cardiac cells, but in all the cells of our body, potassium is the major intracellular ion, whereas sodium and calcium tend to accumulate outside of cells. They're more highly concentrated within the extracellular fluid. Movement of these ions across the cell membrane is determined by several factors. First, the ion's concentration gradient. If there were no other influences, and a channel was established that allowed movement of the ion across, the ion would move from an area of high concentration into an area of lower concentration. So that determines movement. The permeability of the cell membrane to these ions. We said that unless any of the gated channels are open, typically the cell membrane is very impermeable. to charged particles, because it's a double layer of phospholipids. However, the presence of specific ion channels can help facilitate movement of ions across. So again, to repeat, ions are going to be insoluble within lipids, so they're not going to cross the cell membrane easily. They require protein structures embedded within the lipid bilayer, transmembrane proteins, in order to allow the ions to pass into or out of the cell. It turns out that there are three types of protein transport structures that can be involved in ion movement. One type is active transport pumps. We talked about the principal one, the sodium potassium ATPase pump. Okay? It pumps ions across the cell membrane against the concentration gradient. Then you have ion exchangers. These are protein structures which allow for passive movement of ions. Okay, typically it's two or more ions that are coupled together. Their movements are coupled. So the principal ion exchanger along the cardiac cell membrane is the sodium-calcium ion exchanger that allows sodium to move into the cell in exchange for calcium moving out. Or the movement can be in the opposite direction. Calcium can move in exchange for sodium moving out. That's a passive transport mechanism. And then you have ion channels, which allow facilitated diffusion of single specific ions. Now, we said that most of these ion channels are gated. We have a few leakage channels, but most are gated. Here's your sodium potassium ATPase pump. It utilizes energy from ATP, and the way it does so, it has an enzyme present along the protein called ATPase that can break down ATP into ADP and phosphate, releasing energy that fuels the movement of sodium to the outside and potassium to the inside. So because of these active transport pumps, the concentration of sodium is much higher outside the cell than it is inside. Okay? So that if you suddenly open channels that are specific for sodium, sodium is going to tend to move inward. On the other hand, potassium is more highly concentrated inside the cell compared to outside. And so if you suddenly open up potassium-gated channels, then potassium is going to tend to move outside, following its concentration gradient. Let's look at the numbers. A typical intracellular concentration of potassium is 135 millimoles, compared to only 4 millimoles within the extracellular fluid. On the other hand, if you look at the concentration of sodium, it's 145 millimoles on the outside of the cell compared to only about 10 millimoles on the inside. When you have lab work done, they're measuring the extracellular ion concentration of potassium or sodium. So if you had a chemistry panel done this morning, your level of potassium, your potassium concentration would come back 4 millimoles, or close to 145 millimoles of sodium. Except laboratories usually use the units of milliequivalents instead of millimoles. For ions that have a single charge, milliequivalents and millimoles are going to be the same. For an ion like calcium that has a double positive charge, 3 millimoles of calcium would equal 6 milliequivalents. So there would be a slight difference there. Okay? But you can measure your extracellular concentrations just by having a blood test done. And again, note that the extracellular concentration of calcium is much higher than the intracellular concentration. How many people took biochemistry? You're familiar with milliequivalents? Yes or no? Do they not teach milliequivalents in biochemistry or millimoles? Okay, Okay? So for most of our body fluids, particularly when we're talking about single part ions, millimoles and milliequivalents are the same. We talked about passive ion exchangers. So these are transmembrane proteins that are able to keep that sodium in one direction and exchange for calcium in the opposite. Typically, sodium-calcium exchanger exchanges 3 sodiums for every single calcium. And then we talk about ion channels. If this channel were open all the time, this would be a leakage channel. But ion channels are more commonly gated, and those gates are closed. Now, those channels can be activated or opened in response to a change in transmembrane potential, in other words, a change in voltage, or with some channels, with binding of a ligand, a chemical messenger. When activated, the gate opens and the channel opens. And you can have sudden movement of ions across the channel, typically a concentration gradient. So gated channels can either be voltage gated or ligand gated. These are leakage channels. This one's for potassium, this one's for sodium. These are always open. But gated channels are typically closed and open only in response to a certain stimulus. We're going to talk mostly about voltage-gated channels today that open and close in response to a change in transmembrane potential. An important concept is the concept of an equilibrium potential for a particular ion. This describes the voltage across the cell membrane that would develop if only a single ion, a specific ion, could diffuse across that membrane. So let's pretend that that cardiac cell membrane was permeable only to potassium. If suddenly the membrane had channels for potassium that were open, in which direction would potassium move? From the inside to the outside, or from outside to inside? From inside to outside. Let's raise the screen.